Recording in progress.
Okay, so hello everyone. Good afternoon. So for those of you who are oh sorry. Yeah, am I audible now? Can someone just confirm? Okay, fine. So good afternoon everyone. So we are meeting for this discussion hour. So just for those of you who are new and who are joining us for the first time. So I'm Radhika and I am pursuing my PhD in physics from IIT Kanpur, and I'm one of the TAs for this course, the course that you are taking, Essential Mathematics for Machine Learning. And this is supposed to be a discussion session, a 1 hour discussion session, in which we would be solving some problems from some of the previous year's assignments. So for every week, how it is working is every week we solve the previous year's assignments. So last week we solved week 0 assignment. This week we will solve week 1 assignment from some of the previous year questions. So I have the questions written down and then we will start solving these questions. And just a few technical things over here. So for those of you who are new, so the recording of this video that we are having will be shared with all of you, as well as these lecture notes. And all of this discussion that we are having is being live streamed on YouTube, and the recording is also available on YouTube. So I will just share the link of the YouTube channel with all of you in just a minute, so that people who are new can visit the YouTube channel and you can check out the previous year the previous week's video as well, the live stream session that we had last time. So I'm putting it down in the chat box. So this is the YouTube channel, and if you go to the channel you can see the live stream over there. So you can even go and watch the live stream if you find that more comfortable as opposed to the Zoom. And since it is there on YouTube, it will be there forever. So if you miss something in this discussion or if your network goes bad or if you get logged out, no issues, you can go to the same YouTube channel. So this is the same YouTube channel. You can go there and you can subscribe it and turn on your notifications. So every time we have some tutorial sessions or live stream, you will get a notification. So please save this YouTube channel for all future reference. So yeah, so last week we solved week 0 assignment. So this week we will be focusing on topics from the week 1. So this is one of the assignments from the previous years. So we will start by solving. Again, some simple questions are there. So by the way, all your assignments will be multiple choice type questions. So all these assignments that are there are MCQ type, but you should know the concept. So sometimes it happens that if MCQ is there, then we tend to guess the solution, or either by elimination or by some sort of tricks that we use to solve MCQ problems, which is good. I'm not saying it is bad. It is helpful to solve the MCQ questions, but at the same time, I would insist that you also solve the questions thoroughly and step by step properly, so that you exactly know what is happening and how to solve the questions properly, and not just by using some tricks or something just to come up with the solution to the MCQ problem. So here we start with a very simple problem, so to say. So this is a problem on vectors. So the question says that the angle between the two vectors, so we are given two vectors in a three-dimensional space. So the angle between these two vectors, A and B is, so we need to find out what the angle is. So we know this is quite simple. So if theta is the angle between the vectors, then we know that cos theta is equal to A dot B divided by mod A times mod P. This comes from the simple definition of dot product that you would have learned earlier as well. So this is how we will find out the theta. So let us just find out the dot product. So this is 1 times -4 plus 2 times 1 plus -1 times -2, and then mod of A. So mod of A is nothing but square root of 1 squared plus 2 squared plus -1 squared. This is mod of A. Then similarly we have mod of B squared. So this is cos theta, and if we work out the numerator, so this is -4 plus 2, which comes out to be 0. So cosine theta is equal to 0, which implies, this is pretty simple, theta is equal to cos inverse of 0, which is nothing but 90 degrees. So this is the option. So this is how you are going to find out the angle between any given vectors. Next, we have a question on linear dependence and independence. So we are given a set of vectors. These are the 3 vectors we are given: 2h4, 5h2, and 3h0, where h is an unknown. So the question says the value of h, which is supposed to be a real number, for which the set of vectors, these 3 vectors, is linearly dependent, is what we need to find out. So if we recollect our definition of linear dependence and independence, so if we have 3 vectors and if we take a linear combination of these 3 vectors, so let me write down the linear combination. So if we write down the linear combination of these 3 vectors, it will be some A times 2h4 plus B times 5h2 plus C times 3h0. So this is the linear combination, and if we set this linear combination to be equal to 0, then if we try and solve this system of equations, then if this implies that A equal B equal C equal to 0, then we have what is known as linear independence. So what this means in other terms is that if a set of vectors are linearly independent, then you cannot write one vector as a linear combination of the other remaining vectors. So if you take the whole linear combination and if you set it equal to 0, then if A, B, and C all are equal to be 0, then we say that these 3 vectors are linearly independent. And if not, if we have a non-trivial solution, so this, by the way, all equal to 0 is what is called as a trivial solution. Trivial because everything is 0. And if we have non-trivial solution, for A, B, and C, then we have what is known as linear dependence. So this is just simple definition of linear dependence and independence. So you should remember this, what is linear dependence and what is linear independence. So now let us look at this linear combination that we have written down. So if we expand this and if we write the system of equations formed by this linear combination, then what we have is following. So we will get 2a plus 5b plus 3c equal to 0. This is by looking at the first components. So these components, and this should be equal to 0. By the way, I should have written this differently. This 0 is not the correct way I have written. This is a 0 vector. So I should write it as a 0 vector. So this is a 0 vector. So 0 vector. So if you look at the first components, these are the first components, which should be equal to 0. Then we look at the second component. So we have h times a plus h times b plus h times c is also equal to 0. And finally, if we look at the third component, we have 4a plus 2b plus 0c is equal to 0. So we have these set of three equations, a system of three equations in three unknowns a, b, and c. And we can write it in the matrix form as follows. We can write this in the matrix form like so. So this is the matrix form of this system of equations. Now, in order to solve any system of equations, we first write it in the matrix form, and then we use what are known as row operations to solve the system of equations, the set of equations that we have. Now, there are some properties of row operations and why we aren't using IJK. So Himanshu, I don't think I understood your question. What do you mean by why we are not using IJK? That is, IJK is the basis vectors. So when I mean to say, so what you are saying IJK, these are the basis vectors. That means I is essentially 1, 0, 0. J is 0, 1, 0, and k is 0, 0, 1. So when I write a vector, let's say 5, -1, 3, then what this means is 5i minus j plus 3k. So I don't think I understand. Could you please unmute yourself and ask the question that you were trying to ask? Himanshu?
Yes, ma'am. My question is why you aren't dealing in I cap, J cap, K cap, while these are the set of vectors.
Yeah, so we are given these set of vectors. We want to find out the condition for which these three set of vectors are linearly dependent. So we are given these set of vectors. We can be given 10 vectors, 100 vectors, as many number of vectors in any given vector space. And the task is to find out whether those vectors are linearly dependent or linearly independent. Now the IJK vectors that you are saying, these are the basis vectors for the vector space R3. And since they are basis vectors, they are definitely linearly independent. So the task is not to see whether IJK is independent or not. IJK is definitely independent because it is a basis vector for R3. And we are using those basis vectors to represent each of these vectors that we have. But the question is that we are given these three vectors and we need to check whether these three vectors are linearly independent or not. So do you understand the question, what the question is asking? First tell me that, then we will proceed.
Yes, ma'am, I understand the question.
Okay, so what exactly is the question? Can you just repeat it for me so that I am assured that you indeed understand the question?
As in question, these are the vectors. So I think these can be solved by vectors by the lambda thing.
Yeah, lambda thing. So this is the lambda thing only. So in the lecture notes, if they have written lambda, so they would have write lambda I vi summation I equal to 1 to n is equal to 0 if this equation is there, and if this implies that each of the lambda I is equal to 0, then we have linear independence. Is this what you are talking about?
Yes, ma'am.
Yeah, so this is the same thing. So what I have written is in this notation, I've just used a different notation. Maybe that's why you are getting confused. So for me, lambda 1 is equal to A, lambda 2 is equal to B, lambda 3 is equal to C. I just used this ABC notation instead of lambda 1, lambda 2, lambda 3. And V1 is the given vector 2H4, V2 is 5H2, V3 is equal to 3H0. So these are the three vectors, these are the coefficients, and if each of these coefficients are equal to 0, then we have linear independence. So now do you understand it a little bit better?
Okay, ma'am, I got it.
Yeah, you got it. So it is just a different notation. So I think you got mixed up with the notation, I believe. So this lambda I are the coefficients. Here I am taking the coefficients as A, B, and C. What you are calling as lambda 1, lambda 2, lambda 3. And here these are the vectors that are given, what you would be calling as V1, V2, V3. So this is the condition for linear independence that we need to be checking out. So I can just highlight it for you in case if you get confused. Yeah, so just maybe the change of notation, I think probably got a little bit confusing. So it is the same thing. So this is just writing the linear combination. Okay, you can take linear. So A, B, and C are scalars. These are real numbers. So 1, 2, 3, 4 or whatever. So these are just real numbers, just like these lambda i's that we have. So yeah, so we have this matrix form, matrix representation of this system of equations that we have. Now we need to solve this system of equations and see what value of A, B, C we get. If A, B, C equal to 0, then it is linearly independent, but that is not what we want. We want linearly dependent, and we need to find out what the value of H is. Now, before proceeding, how do we solve the system of equations? We apply certain row operations. So, there are some properties of row operations and determinants. So, if we do some things in the row operation, then how the determinant changes, there are some of these properties. I will write those properties out for you for your reference, then we can solve the questions. So what are the row operations? So row operations can be switching the rows, row 1 and row 2 we can interchange. So determinant changes sign upon switching rows. So if we switch rows, then the determinant just changes sign. So if determinant is 5, and if we just interchange two rows of a matrix, then the determinant would be -5. Then the next property is that the determinant is scaled by the factor multiplied to a row. Okay, so if I multiply a row by a number, let's say 2, just one of the rows of the matrix, then the determinant would just become 2 times the original determinant. And the last one is determinant is unchanged upon adding rows. So if I have a row operation, say R2 goes to R2 plus R1, then the determinant remains unchanged. So these are some of the properties. Why I have written them down for you. You will come to know in a minute why these are important. Now what we need to do is we need to solve this system right here. This is the main thing. We need to focus on this. And for a trivial solution after row operations, so after we have applied row operations, for a trivial solution, the reduced row echelon form comes out to be the following. This you can check out for any matrix, and you can try and prove it for you. You can try to prove it for yourself. You will see that in order to get a trivial solution, if we apply row reduction operations to any matrix, and if it comes out to be the identity matrix, only then we get the trivial solution. And easily you can verify this. Why? Because if we have this row reduction operation, then what you get is the following. So immediately you can see A equal to 0, B equal to 0, C equal to 0. So if this is the form of the matrix after row operations in the reduced row echelon form, then you get a trivial solution. But we want a non-trivial solution because we want to find out the condition for linear dependence. So for non-trivial solution, what it comes out to be, I will write that for you. So for non-trivial solution, at least one row needs to be 0. So in the reduced row echelon form, at least one row, at least this last row needs to be 0. The other rows could have whatever numbers, but at least one row needs to be 0 in order to get a non-trivial solution. So in such a case, when one of the row is 0, the determinant of this matrix is equal to 0. And if the determinant is 0, and we know that these row operations either just change the sign of the determinant or just scale it by some factor. So if it is 0, then changing the sign of 0 or changing the scaling by 0 doesn't make sense. It will remain 0 throughout. So the determinant of the matrix needs to be 0 in order to get a non-trivial solution. So what our matrix is 2, 5, 3, H, 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 4, 2, 0, and this determinant needs to be equal to 0 in order to get a non-trivial solution. So let us just find out this determinant in terms of H. So this determinant is 0 is equal to...
One question I do have. So geometrically, what determinant tell us?
Sorry?
Geometrically,
Yeah.
what do we mean by determinant?
So geometrically, the determinant would give you the volume of the parallelepiped formed by the 3 vectors. So if you have 3 vectors in a 3D space, but this is only for the 3D case. If you, or else another interpretation is if you are looking at the cross product or something. So if you have ijk or something in 3D, only in 3D. If you go to 4 dimensions, 5 dimensions, higher dimensions, you do not have any kind of interpretation whatsoever. So like in school, you would have seen that we find out the cross product as follows. We write ijk and then we write whatever the terms are, and then we find out the cross product. So if we have something, this is like a side note. This is not part of this thing. This is a completely off track question, by the way. So this is, I'm writing it down as a side note. This has got nothing to do with linear dependence, linear independence.
Correct. But
Yeah,
we would like to know, right?
Yeah, just give me a second. So if you have some vectors, so you just write down your ijk, you have whatever components. In school, you would have done this. So this basically gives you what is known as the cross product if you have some vectors. And so this is one of the things that you can do with determinants. It can help you give you the cross product. And the other thing that you can do is, so the other thing is if you have 3 vectors, so if you have, let's say, vector 1, so x1, y1, z1, x2, y2, z2, and x3, y3, z3. Let's say these are the three vectors, 1, 2, and 3. Then this is basically the volume of the parallelepiped. So it's a big word, maybe I'll write it below. So this is volume of parallelepiped. Volume of the parallelepiped formed by the three vectors. So if you know what a parallelepiped is like a generalization of a parallelogram from 2D to 3D. So all of you know what a cube is. So
Correct. Yeah.
yeah, in a cube, if you just change the angles from 90 to some other arbitrary angle, and if you change the lengths from that being to be equal to be unequal side lengths. So if you have unequal side lengths, unequal angles not equal to 90, then the shape that is formed is known as a parallelepiped. And the volume of that parallelepiped, yeah, tilted matchbox is a very good example. Yeah, you can just take a matchbox and tilt it and shear it in one direction. Then what you get is a parallelepiped, and the volume of that parallelepiped will be given by this determinant, provided you write it the components of the vectors either as columns or as rows. So that is the thing. Volume of parallelepiped is scalar triple products. Yeah, so that is how you represent it. So this is how you would represent. So if you find out the determinant of this, so this is the matrix, you find out the determinant of this thing, and this gives you what is known as the volume of the parallelepiped. But this only works for 3 dimensions. And given that in machine learning you will be having vectors which are higher dimensional, not necessarily 3-dimensional. In fact, they would be having the basically very high dimensional vectors. So in dimensions greater than 3, you do not have any kind of physical interpretation whatsoever. So this only works when it is a 3D case.
So determinant, you are saying that, let us say that for non-trivial solution, we have a determinant as 0. We require those, right? So
Yeah.
determinant 0 means you get the volume as 0, right? So no volume.
Yeah. So very good point. This is a very good point actually. So I will point this thing out. So you have raised a very nice point. So if we look at what linear dependence means, so let's say we have 2 dimensions. Okay, I will again maybe draw some line out here. So if we are in 2 dimensions, okay, so we are in 2 dimensions. So linear dependence here would mean if you have one vector like this and another vector is parallel to it, so these are linearly dependent vectors. Okay, the moment you have vectors like this, you have in one direction and in another direction, these are independent. So this is dependent, and this is independent. Okay, now we come to generalizing it to 3D. So now drawing in 3D is a bit difficult, but I will try. So now you come into 3D. So in 3D, if you have basically vectors which do not span a volume. So if you have vectors in a plane, so let's say this is my xy plane, x, y, and z. So if I have one vector like this, another vector like this, a third vector like this, all in the xy plane. So all of them are in the xy plane. So this is dependent. Okay. And the moment you move one of the vectors out of the plane, you have 3 vectors which are linearly independent. Does that help?
Yeah.
Okay.
That helps.
Yeah.
Thank you. So considering, right, so let us say that we are going to the n dimensions, and we have the vectors which is n minus one dimension, which are those which are linearly independent, but the last one is dependent on the n minus.
Yeah, if it is in that space, in that subspace spanned by, so now you will not say a plane, by the way, because plane is only 2D, 3D.
Correct.
So you will say as a subspace. So if you have an n-dimensional vector space, and inside that n-dimensional vector space, if you have an n minus 1 dimensional subspace, And if we add the nth vector into that n minus 1 subspace, then they will be forming a linearly dependent set. You need to move out of that subspace in order to form the independent vectors. Yeah.
Okay. Thank you. Thanks.
So, yeah, good question, good point. So, someone is asking, does transposing matrix change the determinant? So, yeah, as people have rightly pointed out in the comments, so transposing the matrix does not change the determinant. So, you could write it as, you could write the vectors as either rows or as columns, given what feels comfortable to you. I find it comfortable writing it down as a column. So yeah, coming back to this question that we have. So yeah, this was a good discussion, good point raised on this dependence and independence. So for dependence, we want this determinant to be 0. And in 3D, as you people pointed out, so dependent in 3D would mean that the vectors are lying in the same plane. So all 3 vectors are forming a plane. So this is the plane right here.
So maybe in the plane, or maybe that could be a collinear, right? In the same line.
Yeah, it could, same line is even more specialized case. But yeah, so they are all in the same plane is the more general way of saying that they are linearly dependent. If it is in the same line, then definitely, of course. So this determinant to be equal to 0, what is the determinant of this matrix? It is 2 times negative 2h. Sorry. This 2 times negative 2h minus 5 times negative 4h plus 3 times 2h minus 4h. So this is nothing but minus 4h plus 20h minus 6h, which is equal to 10h. So clearly you see h equal to 0. So we have solved the question. This part is h equal to 0. So if you have h equal to 0, then you have a linearly dependent set of vectors. And you can see clearly why. So if we put, let me write down the final matrix. So what we are getting is when we put h equal to 0, h equal to 0, 2, 5, 3, 0, 0, 0, 4, 2, 0. Okay, you see this. Now you see that the y component, if we are looking in the xyz picture, if we are following this xyz nomenclature, is always equal to 0. So all these 3 vectors are in the xz plane. Okay, so this third vector is essentially along the x-axis. This is essentially along the x-axis, and these are in the xz plane. So all these 3 vectors lie in the xz plane if you are following this nomenclature. If you are thinking in terms of the Euclidean space, the 3-dimensional Euclidean space, if that is how you want to visualize it, then this is what it would mean. So this solves the question on linear dependence and independence, and this is how you would basically deal with any kind of question on linear dependence and independence. So now we move forward. We have this third question. Another question, this is a question on, we are given a vector space. So we need to see the axioms. So when we write down a vector space, we had written down a bunch of axioms which need to be true for it to be a vector space. So here we are given a vector space and we are defining the addition and multiplication in a little bit special manner, not in the conventional sense that we typically define. So this is how the addition and scalar multiplication is being defined right here. It's a little bit odd, but you can define it nonetheless. And you want to see whether all the axioms are being satisfied, all the axioms that we wrote when we were discussing vector spaces are satisfied or not. So these are the axioms that they have written. This is the distributive property. This is the identity. This This is closure property and associativity. All these axioms need to be satisfied. So we need to see which of the following axioms are being violated over here. So from this scalar multiplication definition, from what I can see, I can immediately spot that something is fishy with this thing over here. So if I write it down, if I write down my unitary law, or essentially what is the identity over here. So the unitary law is saying that there is an identity. If you multiply it with the vector, it leaves the vector unchanged. So now if we take, in our case, if we use this definition right here, so we have 1 times u is nothing but 1 times u1, u2, which if we use this property right here, this definition right here, it says it is 1 times u1 comma 0, and so this is u1 comma 0, and this is clearly not equal to u because our u was u1 comma u2, so this is clearly not equal to 0. So this unitary law is not being satisfied over here, so this is the correct option. You can verify for yourself that the other axioms are indeed true. You can try of seeing the closure, the associativity, the distributive property. So yeah, just try and solve them once on your own. If you still have some queries, then maybe we can look at it. The next question, this is another question on linear combinations. So here, instead of the vectors in the conventional sense, we have vectors in the form of matrices. So any element of a vector space is called a vector. Whether you think of it in terms of your conventional sense of vectors, like arrows in three-dimensional space or not, is not important. In mathematics, every element of a vector space is called vector. So here we have these elements over here, which are matrices, and we need to form linear combinations of these two matrices and see which one of these options is indeed a correct linear combination. So let us just write down the linear combination. So linear combination. So if we write down the linear combination, again, I prefer A, B, C, D. Someone in the beginning got confused with lambda and V1 or something. So just to clarify, I've written A, B, C, but these are just some scalars, some constant numbers, some real numbers, some coefficients to these matrices that we have. Whether you write it A, B, C, D, alpha, beta, gamma, X, Y, Z, lambda 1, lambda 2, lambda 3 is completely your choice. It is just nomenclature or notation. So this is the linear combination that we have, and if we just expand it, we get A plus 2B, then we have 3A plus B, then 4A and 2B. So for any one of these to be a valid linear combination, we need to find out a solution for A and B, and it needs to be consistent. So what we mean by that is, let me just write down. So the first option, from the first option, we get 4A is equal to 12 and 2B equal to negative 2. So this gives us A equal to 3, B equal to negative 1. Now if we look at this column, so earlier I was using this, the second column. So I used this right here to find out the value of A and B. Now I will look at the first column and see if it is consistent or not. So A plus 2B comes out to be equal to 1. This thing right here, if you do, and then if you look 3A plus B, that comes out to be 9 minus 1, that is 8. So it is indeed consistent, 1 and 8. Now we will look at the second option. So from this we get 4A equal to 4 and 2B equal to 2 right here. So this gives us A equal to 1, B equal to 1. And if we check the consistency, we see A plus 2B is equal to 3 and 3A plus B is equal to 4. 3 and 4 right here, so it is consistent. So now we move to the third option. So 4a is equal to 8 and 2b equal to -1. So this gives me a equal to 2, b equal to -12. Now if we do the consistency check, we see a plus 2 times b is what? 2 minus 1, which is 1. And we see no, it is not 1, it is 2 right here. So our consistency check has failed. So this option right here is not a linear combination of these two matrices that we are given. Similarly, you can check out for the option D and you can see that you will find out values of A and B and it will be consistent with the other elements. So you can see that the option D is also a linear combination. So only option C is the one which is not a linear combination. So moving further, now we have some question on subspaces. So the question says, which of the following is a subspace for R3? R3 being the Euclidean space of dimension 3. You can think of it like your XY, conventional XYZ space. So we are given these 4 options and we need to see whether it is a subspace or not. Now, subspace, when we say subspace, so subspace is basically a set of elements, just I'm repeating the definition. So subspace is a set of elements which belong to the vector space and they also form a vector space. So a subspace is a vector space in itself, but it is a subset of the original big vector space that you have. So in order for any of these to be a subspace, all of these need to basically satisfy the axioms that we have for a vector space. Only if they satisfy the axioms of the vector space can we call them to be a subspace. And so let us check one by one if they pass the axiom test or if they fail. So if we look at W1, then in W1 we see that the condition given is x plus y plus z equal to 1. That means the 0 vector 0, 0, 0 is not an element of this set W1. Now, one of the axioms of a vector space or one of the conditions for something to be a vector space is that you need to have the 0 element or the 0 vector. So here the 0 vector is not a part of this because if you basically x, y and z are 0, 0, 0, then adding x plus y plus z does not give you 1. So this 0 vector is not a part of W1. So W1 is not a vector space. Then if we look at this W4, this W4 also right here, it says x, y, comma 1. This is the condition. So this is 1. So again, what we have is that the 0, 0, 0 or the 0 vector is not a member of W4 because the last element in the condition says it should be 1. So W4 also does not have the 0 vector. Now if we look at, let's say, W3. So W3, the condition is that x, y equal to 0. Now let us take some example. Let us say we have a vector 1, 0, 0. This vector is clearly a member of W3. Why? Because x, y product is 0. Then if we have take the vector 0, 1, 0. This is also a member of W3 because again x, y equal to 0. But if we add these two vectors, then what do we get? 1, 1, 0. Now this is not a member of W3 because x into y is equal to 1. So closure property itself is not being satisfied by this W3. So we are left with W2 and you can check that this W2, indeed the 0 vector is there, the 0 element is there. If you set x, y equal to 0, then you have the 0, 0, 0 element which is the member of W2 and you can similarly you can check for the other properties, the closure property, the associativity, the distributive. You can check those axioms, the identity. So these will be satisfied by this W2. So another question on subspaces. So this time the question says, which of the following is not a subspace of M, N, vector. So this is the vector space. Mn means vector space consisting of n cross n matrices where the elements belong to the real number, where the elements of the matrices are real numbers. So this is basically matrices. It means matrices which are n cross n and they have real entries. So we need to see which of these are not a subspace. So let us just take some examples. So just for example, let us say,
Ma'am, one question I do have.
yeah,
So regarding the subspace, right? So there are three conditions we need to check, right? So one condition is that whether the zero vector is inside those subspace or not. Second condition is closure under the vector addition. And third condition is that it's scalar multiplication.
Yeah,
That is closure.
So not just three conditions, you have a whole bunch of condition axioms that are there. I don't remember how many, some 6-7 axioms are there for something to be a vector space. The first one is closure under addition, and second one
first is abelian group formation.
Yeah, the abelian. So what you mean by abelian group, what you mean by something being an abelian group, and what you mean by something being called a vector space, if you list out everything, like each and every point that needs to be satisfied for something to be a vector space, is you definitely need to satisfy your closure. If your closure itself is not there, you don't proceed further. So you need to satisfy your closure property. Then you need to have an additive identity. So that is the zero vector. So if you add something 0 to some vector, it leaves the vector unchanged. So that is the additive identity. Then you also need another identity which is called the multiplicative identity. So the unitary law that we have written. Yeah, so this is for the scalar multiplication. So basically it is like 1 times the vector leaves the vector unchanged. Then you have some distributive properties, distributive over scalar addition, distributive over addition, distributive over scalar multiplication. You have 2-3 properties over there. Then you have about associativity of the addition. So these properties you need to check each one by one for something to be called a vector space.
Yeah, that is for vector space.
Yeah.
But for subspace also
No, subspace is also a vector space. This is what I mentioned at the very beginning.
Correct.
So all the axioms that are there for a vector space, exact same axioms apply to a subspace. So all the list of axioms that you check, you have to check whether something is a vector space. Same axioms, exact same axioms you would use for the subspace. A subspace is no different in terms of the axioms than the vector space. What a subspace means is that the elements are just a subset of the elements in the vector space. Yeah. So all the axioms, so I will write it down clearly so that when you have these notes, you can check it. So subspace is essentially a vector. It's exactly the same thing as a vector space. So all the axioms you need to check, all axioms. And what it just means that a subspace is a subset of the vector space. So elements belonging to a subspace would always be a member of the vector space, but all elements of the vector space need not be a member of a particular subspace. So this is what being a subset means. But all the axioms are the exactly same for vector space and subspace. So you need to check all the axioms: closure, associativity, identity, distributive. All those properties you need to check each and every one of them. Yeah. So you have another question on vector spaces and subspaces. This time it is for matrices instead of the Euclidean space. Okay, someone is asking something. Is this the last question? Unfortunately, no, we have 10 questions. For subspace existence of zero vector closure. I think this someone just asked, I think. Or maybe you only asked. So
just now I asked.
Yeah, okay, fine. So yeah,
second question raised by somebody else.
Yeah, so subspace and vector. I will write in the chat also if people want to see that. Subspace and vector space, all axioms are the same. So yeah, it's not that you only check these 3 axioms or something. These 3 axioms are there just to get you started. If any of these 3 axioms fail, then you definitely know it is not a subspace. But to check something is indeed a subspace, you need to check all of the axioms. So yeah, we come to another question on subspace. So this is for matrices. And just to make our life simpler, let us take an example where n is equal to 2. So we are looking at 2 cross 2 subspaces. Sorry, 2 cross 2 matrices. So let us take some examples. So let us take some matrix A, a 2 cross 2 matrix. Let us take a matrix B, another 2 cross 2 matrix. Now, if you look at the determinant, so determinant of A is equal to 1 and determinant of B is equal to -1. So this determinant is non-zero. So that means both A and B are elements of S4 because determinant is not 0. But if you look at A plus B, then what do you get? You get 0, 2, 0, 0. Now, if you look at this determinant, this is equal to 0. That means A plus B is not a member of S4. So closure itself is not satisfied. So closure fails. That means this thing right here is not a subspace. And you can check that these S1, S2, S3 are subspaces by checking all the axioms. You can't just say, okay, fine, S1 satisfies closure, so it is a subspace. No. You need to satisfy closure, you need to check the unitary law, you need to check the zero, you need to check the distributive, associative, all those properties. So now another question is there on subspaces. So yeah, a lot of questions on subspaces. So we have 2 subspaces of a vector space. And the dimension of that vector space is given. And we are given the dimension of the 2 subspaces also. So dimension of the first subspace is 4, dimension of the second subspace is 5. And we are given some inequality. Like some, this is 5 less than equal to dimension of W1 plus W2 less than equal to 9. So we are given this inequality. And we need to find out the inequality for the dimensionality of W1 intersection W2. What does that take beside A mean? Oh, someone is asking us piche mein. Take beside, yeah. So this is a confusing notation. This is from the previous year's papers. So I have taken from there, from that paper only. So this thing take means transpose. This is transpose. Yeah, different people use different notation. So in last year's assignment problems, they use this apostrophe to denote a transpose. Now they are using T to denote a transpose. Different people use different notations, but both of them are very well accepted notations for a transpose. So yeah. Coming back to this. So we have basically a property of dimensionality. I will write it down for you. So we have this following property that if you have 2 subspaces, the dimensionality of the sum of the subspaces is this thing right here. I will write it down. Minus dimensionality of the intersection. So this is the property that we will use to solve this question. So if we start with this thing over here that is given to us. So we have 5 less than equal to dimension of W1 plus W2 less than equal to 9. Now we will use this property to replace this thing. So 5 less than equal to dimension W1 plus dimension W2 minus dimension W1 intersection W2 less than equal to 9. Now just put in the values. We are given this 4 and 5. So like so, and then just keep simplifying. So if I just subtract 9 from both the sides, so because this 4 plus 5 is equal to 9, if I just subtract from both the sides, I get the following. Now if I just get rid of this minus sign, then the inequalities will flip their sign. So I will get the following. So this solves the question. Simple question based on this property. You need to know this property. So that means 0 less than equal to dimensionality of the intersection less than equal to 4. So this is the correct option. Now this is a very simple question. So this question says, if V is a vector space of finite dimension n, then which of the following is not true? So the very first thing over here, right here, is not true. Why? Because if you have n-dimensional vector space, you will have at most n linearly independent vectors. So in 3-dimensional space, you can have only at most 3 linearly independent vectors. What someone in the beginning said, ijk. So if you look at the Euclidean space, ijk is the 3 independent vectors. You cannot have 4 independent vectors in a 3D space. So the very first statement right here is completely wrong. And you can see that all the other statements are right. Any linearly independent spanning set of V is a basis of V. Yes, indeed, it is n-dimensional and it spans the vector space. So it is indeed a basis. Any two basis vectors of V have the same number of vectors, and the number of vectors would be n because it is n-dimensional vector space. So this is true. If we have V1, V2 up to Vk as an linearly independent subset of the vector space where k is less than n, then so this is the S. So this thing right here is S, what they are writing. Then S can be extended to a basis. So yes, indeed. So we have k less than n linearly independent vectors. You can add more vectors to it to make it n linearly independent vectors. So this is also a true statement. Only the first one is false. And now we are coming to the end. So we have just 2 more questions left. So this is a question which says that we have a vector space of 2 cross 2 matrices of real numbers. Then let the subspace U consist of those matrices whose second row is 0 and subspace W consists of those matrices whose second column is 0. Then we need to find out the dimension of this. So let us just write down. So U is basically set of matrices whose second row is 0. So you have, let's say, A, B, some numbers, and then 0, 0 for the second row. So these are the elements of U. So these elements belong to U. Then for W, you have the second column 0. So you have CD 0, 0. So these elements belong to W. And if I write the basis of this, so basis, you can clearly see that the standard basis for this would be these 2 vectors. Using these 2 vectors, you can get all elements in U. And for W, you would have the standard basis as follows. Like so. And you can see that the number of elements in the basis is what is the dimensionality. So if 2 elements are there in the basis, then the dimensionality is equal to 2. So dimensionality of U is equal to dimensionality of W, which is equal to 2. Now if we look at U intersection W, so what would that be? Now intersection would mean that the second row is 0 and the second column is 0. So second row 0 and second column 0. So we are left with just the first element. So for this, you can easily see that the basis is just one dimensional. We have just one element. So that means the dimensionality of U intersection W is equal to 1. Now again we will use this property right here that I had written earlier, this property over here. So we have like so. Now we know the values of these, so we will put in the values. We have 2 plus 2 minus 1, which is equal to 3. So this is the correct answer. Now we have the last question, which says that we have a matrix which is 5 cross 7 dimensional, and the rank of this matrix is 3. So we need to find out the dimension of the null space of M. So how we will do that? We will use what is known as the Rank-Nullity Theorem. What does the Rank-Nullity Theorem says? Rank-Nullity Theorem says that the rank of M plus nullity of M is equal to number of columns in M. So we have all the values over here, so we can put in the rank of M plus nullity of M is equal to 7, number of columns in M. So it is a 5 cross 7, so 7 columns would be there. Rank is given 3, so 3 plus nullity of M is equal to 7, which implies that nullity of M is equal to 4. So nullity is what is the dimension of null space. So this is equal to 4. So this is the last question. So it is based on this rank nullity theorem that we have. So these properties are very helpful properties where the notes is, ma'am, as a pointing in mistake. Yeah, there is some mistake. Okay, let me see. 4 minus 1. Oh, sorry. Thank you for pointing it out. Yeah, this is 4 minus 1. Yeah, thank you for being cautious. I really appreciate this, Rohit. So yeah, thanks for pointing it out. Yeah, I selected the correct option, but I wrote over here the wrong thing. So this is 2 plus 2 minus 1, which is 4 minus 1, which is equal to 3. So the answer to question 9 is 3, the dimension of U plus W, this option. And this. So yes, so the so basically 2-3 important points from this assignment that I would say is number 1, what is, I will just summarize everything for you, what take away from.
Ma'am, the nullity, can you please define in terms of that space, the dimension of null space, right? You said the dimension of null space of the given matrix is 4. What does that mean actually? Can you give the example?
Sorry, so I didn't understand. So nullity, someone has shared something. Yeah, this is the Google Drive where I will be uploading the lecture notes. Yeah, but so coming back to this, so nullity is the word which means the dimension of the null space.
So what is the null space here?
So
in a matrix, what do we mean by null space?
Okay, I will explain the null space, but before that I would like to ask, means have you watched the lectures on
yes
the
I have watched
vector space and
vector space and all those I have watched.
Okay, so null space is basically that space which maps to 0 elements. So you have a linear transformation, and so a linear transformation takes in some vectors and gives you some output vectors. So if the output vectors are 0 vectors, then whatever the input vectors are called as the elements of the null space. So this is there in the lecture on linear transformations. So if you do not know which lecture this is, what I'm talking about, so this is in the lecture on linear transformations.
Okay, this is linear transformation.
Yeah.
Okay, that is still I need to complete.
Okay, fine. So I will define it for you. So that means this question will be a little bit difficult for you to understand right now. This question is based on the linear transformation, but I can give you some 2-minute summary of this thing. So a linear transformation is basically like if you have, I'll just give you like a brief summary. You can go and watch the lecture in detail. But just so that you understand what we are doing over here. So if we have two vector spaces, V and W. Okay. So a linear transformation is an operation which takes elements from V into W. So we have, let's say, some elements in V. We have some elements in V. We have some elements in W. So it is like a mapping from this V vector space to this W vector space. So one of the simplest mappings that I can tell you is, let's say, just scaling. So if you have, let's say, a vector space of real numbers, okay, in the two-dimensional space, and you are taking it again to the two-dimensional vector space. Let us say my V equal to W is equal to R2, okay. I am looking at the XY plane. XY plane. So one of the simplest operations can be just scaling. So if I have a vector, then I will just scale it by 2 times and make it twice the length. So if I have x comma y elements, and if I take it into 2x comma 2y, then this is what is known as linear transformation. So you have let's say elements 1 1 in R2, this goes to element 2 2 again in R2. So this is like just the function. So in normal, you would have learned what functions are, right? F of x, function of x.
Correct.
So these linear transformations are like those functions. You take some element and you transform it, and then you get another element. So this is like what linear transformations are, and you can represent each linear transformation as a matrix. Okay. So so you have the matrix representation of the linear transformation. So let us say this linear transformation that I have written right here can be written as follows. So you will have input vector. So the matrix of this linear transformation that I just wrote, the scaling, is as follows. Yeah, so you see 2x and then you see 2y. So this is the matrix of the linear transformation. So every linear transformation can be written in terms of a matrix, like I've just written down. So this matrix, so what they are saying is that you have a linear transformation which is given by this 5 cross 7 matrix. So here I had taken same dimensions like R2 going to R2, but I can take it from, let's say, some vector space which is 7-dimensional to some vector space which is 5-dimensional. Then the matrix that I will have will be a 5 cross 7 matrix. So for this, we will have a 5 cross 7 matrix. So this is that matrix, and the rank of this matrix is 3. Then we need to find out the null space of M. Now null space is, so if I have some matrix, so if I have a matrix and if I multiply, if I operate it on some vector and if I get 0 0, if I get the 0 vector, then all these elements are members of the null space. Okay. So here in this case, you will see that the only element in the null space is 0 0. Only the origin remains unchanged by this scaling thing. So here this is the null space.
The side would be 1.
Yeah, so this dimensional is 0 because it is the 0 vector.
Okay.
Yeah, so this is dimension 0. So this is what the dimension of the null space means. And this is some Rank-Nullity Theorem is there. If you watch this lecture on linear transformations from week 2, I guess, then you will know what this thing is.
Yeah, thanks a lot.
Yeah.
Oh, one thing more, one more question.
Yeah.
Probably a very naive question.
Mm-hmm.
So consider that we are going to transform something, right, from matrix n cross n to some matrix, right? So probably n cross n. Whether there is a way that we can transform the matrices from n cross n to n plus 1 or n plus 3 in the higher dimension, whether such kind of possibilities there.
Okay, so just a minute. I'll keep that question on hold. I see some things are going on in the chat. So let me just attend to those questions and then we can come back to it.
Sure.
So somebody wants to know where the notes are there. So yeah, someone has shared it in as the Google Drive link. You can even go to your NPTEL portal. In the NPTEL portal, there is something known as problem solving session. If you click on that problem solving session, you will basically get all the notes and the videos. So you can go to that NPTEL portal. When someone is saying next Saturday we'll be solving assignment 1 and assignment 2 of current semester. Sorry, I cannot solve the current semester assignments. I am told not to do so. Current semester assignments are not supposed to be solved in these discussion sessions. But what we are supposed to do and what we can do to help you is to solve the previous year's assignment questions, and you will see quite a few similarities from the previous year assignment questions in the basically most of the I have seen, like I have checked some of the questions. For example, I have seen one question on Rank-Nullity Theorem, a very similar question in one of the assignments in the current semester. So once you know what the Rank-Nullity Theorem is, once you can solve this question number 10, you can solve that question from the current semester assignment. Just the values are different. So I will be solving the previous year's assignments and they are quite similar to what the current semester is, but I can't really solve the current semester even after the deadline. So I will ask the instructors if they want to use some of those questions from the assignment in your midterm end term exam. If they want to do that, then sorry, I don't think I can solve it. But if they plan to not use that and come up with something different, then we can definitely solve those questions. So yeah, this discussion session is for solving the previous year's assignments, and they will be very similar to the current semester assignment problems. That much I can say. I've seen some of the questions. They are quite similar to some of the previous year assignments. So yeah, now coming back to someone who was asking some question. I forgot what the question was. Can you please repeat that question? Some transformation matrix, something you were saying.
Yeah, the question is that consider there is a n cross n matrix, right?
Okay, wait, I will write it down side by side. What you are saying, we have an M cross N matrix.
Yeah. So now we know that we can transform it into the lower dimension. PCA is one of the way. So
you have, let us start simply. 3 cross 4 maybe. Okay, just some examples. So 3 cross 4. Okay, so let us say we have. Now what is your question?
So question is that can we transform it to the 5 cross 6 or something in higher dimension?
So you want to go from here into something like this. You want to go from 3 cross 4 to 4 cross 5. You want to add certain elements or certain dimensionality. Okay, I don't think like I have never really come across this thing. So yeah, means as of now I don't think I'm aware of anything like this. So I don't really understand what you mean by this operation. So what this
No, I got your point. The point is very clear over here. We are going to use this transformation in order to reduce the dimensionality so that we will have the clear picture. We want to reduce something which is very dependent, and that's why we use the transformation, right? Changing from one dimension.
So no, so I think you are either I am not getting the point or you are mixing up two concepts over here. So this 3 cross 3
reduction, we know that is currently we do in machine learning and all those stuff. We are learning right now, right? So reduction of dimension is existing through the transformation. Now the thing is that whether mathematically it is possible to increase the dimension.
Okay, so if I get this thing correctly, so if this is the matrix, then this is like we are moving from a vector space of 4 dimension to a vector space of 3 dimension, okay? This is a vector space of 5 dimension to a vector space of 4 dimension. But it is also possible that we have a linear transformation like this. In this, we will have a 3 cross 2 matrix, if that is what you want to know. But this is for linear transformations. This is not for the reduction or expansion of matrices as such. This is for vector spaces, the linear transformation between 2 vector spaces.
Correct.
But this thing that I think you are not concerned about this. I think you want to do something like, I have a matrix which already represents some linear transformation, and I want to go to another matrix which represents some other linear transformation between some other 2 vector spaces, and you want to kind of connect these two. Is that what you want to do?
Yeah, means actually I like to transform this one, the left side one, to the right side one. So that
you know how to go from this to this, you are saying?
This to this, yeah, this to this, we know, right? The transformation is possible.
Okay, so maybe if I have some option of sharing some whiteboard, if you want to write something for me, who can share whiteboard? All participants, okay? Let me try this. If you can write something, and maybe that would be... Can you see some whiteboard?
Yeah, I can see.
Can you write on this something? Yeah, if you want, you can write on this, I think, to better try and explain what you know and what you want to know. Can you just try writing something out here? So by the way, for others over here, the session is complete. You are free to leave, and for those of you who missed it, I have put the YouTube channel link again. You can go there, and you no need to stay over here. And anyway, we will wind this up in like 5 to 6 minutes. So yeah, you can go ahead and try writing something on this whiteboard and see.
Thank you, Monica.
Yeah.
Writing means what should I write? The
Yeah,
text?
what you want to, what you know, means what you want to do exactly. I don't think I'm able to understand.
Yeah, mainly the basic idea is that consider that we have a matrices, which is consider that M3 cross 3, 3 cross 3 matrices.
Okay.
Okay. Now there is a transformation which we know that we can transform it into similar M3 cross 3 cross 3, which is certainly possible. We do it.
Yeah.
You have just told us, right? It's a possibility. And there is possibility that you we can transform this to lower dimension as well. And consider that we are transforming it to 2 cross 2. That is possible. Now M3 cross 3. Now my question is that M3 cross 3 to, let us say that you want to add certain dimensionality, right? In the matrix. So whether we are currently, is it mathematically possible to add those? We are reducing it, so there could be a way to similarly gaining those information which we have lost, right?
Okay.
So here we are losing information.
Yeah, so mathematically you can do just about any abstract definition you can come up with. So mathematics, anything and everything is kind of possible if you just define something. Physically, whether it has some interpretation or not is not important for mathematics people. So just like I talked about the linear transformations, okay? So I talked about linear transformations. Now, if you have your vector space V, which is the set of all 3 cross 3 matrices, so this is M3. So the dimensionality of this, is 9. Okay, you have 9 elements in the basis.
Correct.
And then if you want to go to another basis, which is M2 of 2 cross 2, so the dimensionality out here is 4 because you have 4 elements in the basis. You can have a linear transformation. I'll just write it LT for short. I'm tired of writing this big word again and again. So yeah, we'll just write LT for short. Understand it is linear transformation. We can have a linear transformation which goes from this way to this way. You can define anything. So for example, I define it like some sort of a projection maybe. So if I have this kind of matrix, then I can define it that I just delete these rows and I kind of come up with something this. This is what I define. I can define this kind of a transformation. Whether it means something significant, I really don't care. It is the definition that I have. Now, similarly, in the same nomenclature, you can indeed come up with a linear transformation where you have V, which is set of 2 cross 2 matrices, dimensionality 4, and you want to go to W, which is 3 cross 3.
Radhika.
Yeah.
Actually, I'm not able to see your screen because this.
Sorry. I think this whiteboard thing is causing the problem. Is that the thing? Let me stop this whiteboard business. To move to trash or something. How do I get out of? Now can you see?
Yeah.
Okay. Yeah, so sorry, I will repeat it. So this is what I wrote. So linear transformation moving from M3 to M2. So this is the kind of transformation that I can define. Like I can just define this kind of a linear transformation. That you take a 3 cross 3 matrix, you construct a 2 cross 2 matrix out of it by just taking this 2 cross 2 sub matrix. So I can just define it. It may not mean anything significant for me physically, computationally, whatever, but I can define it. Similarly, in the context of this linear transformation only, in nothing else, in just this context, if we start with the matrix of 2 cross 2, the vector space of 2 cross 2 M2 matrices, and we can go into the matrix of 3 cross 3 M3 matrices. So we are going from dimension 4 to dimension 9. It is in the sense of linear transformation. So note that. So how I can do that is I can just define. So I have A, B, C, D. Okay. And then I define that I will take this into A, B, C, D. And I can say over here 2 times A, 2 times C, 2 times A, 2 times B, and 0. This is a definition that I've come up with. So this is the linear transformation. So you give me a 2 cross 2 matrix. This is the 3 cross 3 matrix that I want to construct. Whether it means some significant operation or not. For example, I gave you a significant.
No, I can give you the significance.
Okay.
So example is, consider that you have a image of 3 cross 3. You want to expand it, right?
Mm-hmm.
So you will fill some pixels, right?
Yeah.
On that matrices. So you have to learn something about those pixels, and you need to fill similar kind of pixels, right? So that you can expand your matrices over there.
Mm-hmm.
So that is a example.
Yeah, then some sort of interpolation techniques you would need to basically apply to try and kind of fill in those gaps that you are creating by trying to expand something. So yeah, means mathematically it is possible to define something, but
no, that is pretty good. Means I got the idea about your trying to say.
Yeah. So for the
it.
physics, you need to really try and see if you have some application, some physical some interpretation of that or not. But mathematically, yes, indeed, it is possible to define some linear transformation from a lower dimensional vector space to a higher dimensional vector space.
Correct. So probably the way you are writing, right, 2 and all those can go down. Yeah, 2A, 2C, 0, and 2A, 2B.
Yeah, just something I have come up
Something,
with.
right?
Yeah.
So probably we can learn those and we can write to explain. Like,
Yeah, could be.
learning
Not
could be.
could be. Not that I am immediately aware of this thing. So maybe I can try and find it out and we can discuss this maybe in the next class. Not that I'm offhand aware of anything like this that we would be doing or not.
Thanks.
Yeah.
I just had a doubt.
Yeah.
So, what do you mean by adding two subspaces of vector spaces? Like, we had that equation of dimension of S1 plus dimension of S2, that equation we wrote.
Yeah.
Yeah,
Something.
dimension of U plus W.
Yeah, somewhere here, right? This one, this guy.
Yes, right there.
Hmm.
So, does U plus W signify the union or it is the component-wise addition?
So it is the direct sum. So it is like the component wise stuff that you have. So it is not a union. Union would be if you want to write a union, union W. This thing would mean so it would mean that so intersection is like both of these things would be 0. Union would mean you have these elements and you also have these elements. So essentially what you would get then is that you would basically have only a 0 over here and then you will have some elements over here like this if you take the linear combinations of these.
Okay.
Yeah.
Yeah, but we can have subspaces of different dimensions also, right?
Yeah, you can have subspaces of different dimensions as well.
So how will you add them?
Yeah, you would not really add them in the sense of the normal addition that you are familiar with. So it is a concept called like a direct sum is there. So maybe you can check out this lecture. I don't remember which lecture in which it is given. This concept of a direct sum is there. So we do not really have much time right now. So we have already overshot quite a lot. Maybe I can discuss this thing in the next class before we start anything else.
Yeah, sure.
Okay. Yeah, so I hope everyone is like, so everything is done over here. This was next week. We will do the next assignment, but before that, maybe we will discuss this question 9 a little bit more for people to understand. So I will discuss this a little bit more. Okay then, thank you people. So see you in the next week for the next assignment as well as for this subspaces.
Thank you.
Okay, bye bye.
Recording stopped.